Today, I would like to show you CoverBee. CoverBee is a tool to collect code coverage for eBPF programs. So let's get right in. What is code coverage for those not in the know? Basically, what you're looking at is a code coverage report, and it shows you which lines of code have been executed during some sort of event. Most of the time, this would be a unit test or integration test or some other kind of test. And we use this to show us how well our test is covering the actual software that we want to test. There are multiple forms of this, but it's all pretty much the same. You get this red, green, and sometimes gray representation on typically source code, and it gives you an intuitive sense of how well you're doing, and sometimes it shows you the exact amount of coverage that you have. So how does one go about making such a thing? So from the user perspective, this is typically done at the compiler level, or some special tooling that does this for you, and they basically instrument your program to collect this for you in the background. CoverBee is slightly different in that it is based on the actual bytecode, this assembly, but the same principles apply. So our code can be divided into basic blocks. So this is a diagram of having basic blocks where all of the code within or instructions within a block execute together. And then we can say, okay, we know that if we hit in a block 1, then we can color all of those instructions or all of the lines associated with that block. We can color that green in our overview. So for eBPF, this diagram looks something like this. So this is same concept, but slightly differently rendered, and with the actual decompiled instructions. And I know that the diagram on the left is hard to read, but it is there to visualize that this can get quite big and quite complex. But on the right is a more simplified example of something like this. So now that we have identified these blocks, which is quite simple, we just look for branching instructions or changes in control flow, jumps in the code, such things, where we don't have a contiguous list of instructions, and then we say this is a basic block, and within CoverBee, each block gets an ID. Now we need to instrument it, and what CoverBee does is it works on the instructions itself. So I have here an example program, which takes the input of the program, adds a constant to it, and then checks if this number is greater than 22. If it is, we return 2, and if it's not, we return 1 from this program. So quite simple. And if you were to look at it yourself, it consists of 3 basic blocks. And then what we do is we create the right side representation of this. So the teal part of the code basically instantiates our cover map. So we have one BPF map, which we use for all of our coverage data, but we have to get an actual pointer into the map value for us to be able to work with it. So what we do is at the start of the program, we do this once. And we get the pointer, we perform a map lookup for the key 0. So our map only has one key 0, which is a very large value size, exactly as long as or twice as long as the amount of basic blocks. And then we place this in the stack, in this example at 120 from the stack frame pointer. Before this, we store R1, which is the only register in value in R5, and we place this back. And because in this case we are able to analyze the code and see that only R1, R2, and R0 are in use, we know it's safe for us to use R5 and R6 to perform our measurements. So for every, the blue part of the code is for every basic block, we add these specific 3 instructions. In the optimal case, we'll get to that more later. So we copy this same map pointer to the map value. We get it from the stack. We place it on R5. We increment the position to get us to the basic block we actually want to measure, and then we increment that value on the map. So we write to we take the value, add 1, and write it back to the map. This happens for every block, and every block has a unique index within the map, which corresponds to the ID of that block. If registers are in use, so in the worst case scenario where all registers are in use, we need to do a little bit more. So in this case, we determine that we want to use R1 and R2. So the first 2 instructions basically save these registers to the stack. Then we can use them in the exact same way. So we take our pointer, go to the index for this basic block, add 1 to the number, and then we write that number back to the map value. And then the last 2 instructions reapply. So take the register values from the stack and reset them as if nothing happened. And in this way, we can instruct our basic blocks. So this only happens if these registers are in use, which we do based on static analysis. So with that data, we get the following. So we can now color our actual assembly based on what we recorded. But for most people, this is not very readable, not very nice. So there is a trick to go back to source code, which is BTF line info. So in this case, I dumped part of the BTF line info with the BPF tool for this program, and it shows and these lines which start with a semicolon, they are the lines of the actual source code lines where these instructions came from, and we can use these to map back to the actual source code. So in a naive, so we can then start painting our sources. So this is the part of the source code, an abbreviated part, for example. And what we can do is with this naive technique is we can start coloring, applying the coloring that we had for our instructions to our source code. But you'll notice that our compiler didn't have line information for every single line in our program. This is due to optimization or just simply it not being there for some reason. So what we can do is we can then use the AST to start making conclusions for us. So we know that, for example, that if the first line executed, then the second line also must have executed. Just logically, based from the AST, there is no branching statements here, no ifs, no jumps, whatever. So we can use the AST to do a few things. We can infer which lines were and were not executed, or which were evaluated in the cases of if statements, for example. And we can also remove lines that have, for example, the curly braces or the comments, which gives us a way more accurate percentage if we were to just distill this down to a percentage of work. So we use a C parser for this to apply it back. which is currently the only thing that CoverBee supports, but we could add more languages. So let's see this in how this works. So I have my VS Code open here, and I'm in the CoverBee repository. And actually, what I'll do is I'll go ahead and delete the result I'm expecting. So I'm deleting this HTML file, and I'm also going to delete this file for now. So they're in the example, and anyone can show you, anyone can access this in the repository. And we have here a decent program which has a few maps that collect statistics for. So we can so it's an XTP program, and it collects how many bytes and packets for UDP, IP, and TCP were received. So it's a classifying program, and I won't go very deep into this because of time constraints. So I prepared this demo.sh. What it does is it removes some previous state. It builds the latest version of CoverBee that we have currently checked out, which is master. And then the first thing we do is we load the instrumented program. So we give it we have to compile an ELF before, which is already done in this case. We provide the program that the BPF program we want to load, and we have to pin it. So what we do is we always pin the program in a directory, and we will pin our additional cover map. So this map that has been added on top of all of the things that are in the ELF. And then lastly, we have this block list for which records in between accesses to the program what the actual block analysis is that we did. So which block IDs map to which parts of the source code. We do this, and then after our instrumented program is loaded, we can just run it, do stuff with it. In this case, I'm using BPF tool to do a proc run, and what I'll do is I'll run the firewall program that's in here with some data. So I have a data envelope, which is a packet, and I'll repeat this 2 times. So we can see how many times certain code gets executed. So that happens, and after that we collect the information. So you could also imagine just running your program normally, or running more complex test scenarios, whatever. You can. This is where your tests are happening. And then lastly, we take the contents of the block list and of the coverage map, and we generate an HTML output, which is our report. And it's also possible to generate a Go coverage report directly, which can be used for other tooling. So if I run this, I need to provide my sudo password. Once I do, you'll see that 2 files are created. So the first one is the block list. So this is again it's just a JSON file with a big array of blocks, and it maps these blocks to the line and the column where these happened, and and these will be used to generate the result later on. But for all purposes, this can just be opaque, just as long as you pass in the same block list to the load and the cover source command. And what is generated is this HTML document, which I will open in the browser. If I can find it. And if I go back to my browser, we open this, we can see at the top that we detected a 45% coverage of this, and it colored in the lines that were actually executed. In this case, because I only had 1 packet, it will go to the handle IPv4 twice. It will go to the handle IPv4 twice. And then if we go up here, so we didn't have any IPv6, which is all red. And then in the IPv4 case, which we would expect, and this is all colored. So we did evaluate for UDP, but that was not true. And it did go into the TCP case here, and then it incremented the values there. And here we can see that this gray part, the slightly grayed out part, is a 1, so it's this has been executed once, and then this one was also executed once, and this is because in the first instance we create a map key, and in the second one we just modify it. So it gives you potentially really nice information about your BPF tests, and in this case we should test for UDP and IPv6 to get more complete coverage. So that was all. Thank you so much. You can find the CoverBee at the link below, and I hope you have a good rest of your eBPF summit. Thank you.